The Pennsylvania State University, College of Earth and Mineral Sciences, Department of Energy and Mineral Engineering presents the Electrochemical Laboratory instructional video, Corrosion Measurements. In this video, we will demonstrate how to perform corrosion potential measurements and how to use the techniques linear polarization resistance and linear sweep voltammetry to estimate the corrosion current of a steel sample. Here, we will again use the RDE to control the hydrodynamics of a test solution in contact with the metal sample. For our tests, we will be estimating corrosion properties of a steel sample in an aerated acidic solution.
Equipment and materials.
A computer-controlled potentiostat for performing the electrochemical techniques. Test solution. An aerated 1 mole per liter sulfuric acid solution to simulate a corrosive environment. In this lab, 3 electrodes will be used. The first electrode is a steel RDE working electrode that will be made using a sample RDE kit. The second electrode to be used is a platinum counter electrode. And the third electrode is a silver chloride reference electrode. A glass electrochemical cell with a rotating shaft for the working electrode. A speed controller for the rotating shaft. Remember that under no circumstances should the controller be set to a speed above 2500 RPM.
Preparing the steel sample RDE.
Using the same polishing techniques outlined in the LSV RDE lab, we will first polish the steel sample until it has a mirror finish. Place the steel sample face down on the polishing cloth and firmly press the PTFE sample holder onto the steel sample. Secure the steel sample into the sample holder, then use the metal probe to apply pressure to the steel sample and gently polish the exposed surface. After the surface is sufficiently polished, rinse and wipe the surface using the appropriate techniques previously outlined. Once the surface is clean, carefully remove the sample from the holder and place it into the second PTFE cylinder of the sample RDE kit. As needed, use the metal rod to position the steel sample to the center of the PTFE cylinder with the polished face down. Next, firmly press the RDE tip onto the steel sample. After the steel sample is wedged into the RDE tip, finish positioning the steel sample with your finger until the steel is flush with the PTFE on the RDE tip.
Cell assembly. In this section of the lab video, we will demonstrate how to properly assemble an electrochemical cell for corrosion studies.
First, all electrodes and the glass cell must be cleaned, rinsed, and wiped dry using the proper procedures established in previous videos. Using a clean funnel, pour the test solution into the glass vessel. Next, insert the counter and reference electrodes into the open ports of the glass vessel. Lastly, take the sample RDE tip with the spring-loaded metal rod placed inside and gently screw the tip onto the rotating shaft. Unlike the platinum working electrode used previously, take caution when screwing this RDE tip into place. Avoid over-tightening the RDE tip as it will eject the sample into your solution. As a general rule, only screw the RDE tip until the clear polymer just covers the first PTFE lip on the rotating shaft. Once the RDE tip is attached, while still maintaining a flush surface, gently lower the RDE into the solution until you see the tip submerged to the red rings. Connecting the leads. After checking that the Gamry potentiostat is turned on and connected to the computer, it is time to connect the leads from the potentiostat to the electrochemical cell. Connect the blue and green leads to the RDE shaft as they are the working voltage and current leads. Connect the red lead to the counter electrode using the alligator clip. Lastly, connect the white lead to the reference electrode and leave the orange and black leads disconnected. And also make sure they are not touching any electrically conductive surfaces. Corrosion potential measurements. In the next few sections, electrochemical measurements related to corrosion of a steel sample rotating at 500 RPMs in an aerated acidic solution will be made. Before running any tests, turn on the speed controller and turn the knob until the shaft is rotating at 500 RPM. Before each test, check the tip of the RDE for any bubbles that may have formed or become trapped on the surface. If bubbles are found, the easiest way to remove them is to raise the RDE tip out of the solution, then slowly lower it back into the solution. Increasing the rotation rate almost never removes bubbles trapped on the surface, so do not attempt this. For all measurements in this lab, the Gamry framework software will be used. The first step is to open the Gamry framework software on the computer and select the Experiment tab in the upper left section of the window. Go down the list of options to the Utilities option labeled A. From the sublist, select option 4, Open Circuit Potential. After selecting the Open Circuit Potential, or OCP test, you will need to change the out file name to OCP steel sample followed by the date and your initials. Check the values in the total time, sample period, and stability boxes, then change them as needed to match those shown on the screen. Once the settings are properly filled out, click on the OK button to start the test. Once the test is running, observe the trend of the recorded data and check to see that the measured potential does not change by more than 3 millivolts over the span of 5 minutes. After the test is completed, press F2 to save the data and continue to the next test. If the measured potential drifted by more than 3 millivolts, then rerun the test as needed until a stable potential is reached. Linear polarization resistance. In this section, we will run one of the most common tests used to estimate the corrosion current via electrochemical techniques. A test suitable to run linear polarization resistance, or LPR, can be found under option B, Physical Electrochemistry, titled 6, Linear Sweep Voltammetry. As before, modify the output file so that it can be easily found later, then proceed to change the settings to match those on the screen. A key difference between LPR and LSV from a test perspective is the range that is scanned from the potential. For LPR, the scan range is usually within 10 millivolts above and below the corrosion potential, or EOC as labeled in the settings. The advantage of this technique is that it limits the polarization of the sample to values close to the steady state potential, E core. The main disadvantage is that the TOEFL slopes cannot be determined from the resulting data. As previously, press OK to start the test and F2 to save the data once the test is completed. Next, we will perform linear sweep voltammetry, or LSV. If the large polarization needed to perform an LSV are not considered to be too destructive, then LSV data collected can be used to estimate the corrosion rate and quantify the TOEFL slopes. First, modify the output file name, then update the test parameters from the LPR values to those displayed on the screen for an LSV test. Remember to press F2 to save the data after the test is completed. Disassembly and lab cleanup. Before removing anything from the cell, turn the rotator speed to 0 RPM and turn off the speed controller. Next, make sure the potentiostat is not running any tests, then turn off the potentiostat. At this point, it is safe to disconnect all electric connections, remove the electrodes from the solution, and follow the standard practices of cleaning the electrodes and collecting all the rinsed solutions for safe disposal. For the sample RDE tip, disassemble the tip, remove the sample with the metal rod, and thoroughly rinse all parts prior to returning them to the storage container. Ask the supervising student if the used test solution should be saved for future use or disposed of with the rinsed solution. Before leaving, clean any glassware used and make sure that everything is put back to where it was originally found.